How's it going, Sophie?
Pretty good. How are you?
All right. So
Good.
this is probably about the maximum class size. We might get a few more people coming in, but it's a small section for the afternoon. So if you want, I'm gonna say go ahead and I'll let you talk to the class about the program and see what questions they have and so on.
Okay. All right. Good afternoon, everyone. My name is Sophie Lin. I'm a professor from the physics department, and currently I'm also the advisor for the Aerospace club. Today I'm here to tell you a little bit about this program and this club. This program was funded by ASCC student government, and from my perspective, I think it's one of the best clubs you can find at Clark College. Depending on the funding, we usually have 2 to 4 teams, and this year, due to pandemic, we have 2 teams. We have ESI team, which is also called the Rocky team. We also have AUVSI team, which is also called the Joint Plan team. Currently, with the Rocky team, we have about 6 students working on a project, a payload project. And last Wednesday, they just finished the payload project, and they're about to ship the payload to Colorado for a real flight test. In this team, we also offer students opportunity to do some kind of certification for the high power rocket certification. And students will be able to learn the basics about building rockets and also the skill that you need to know in order to build rockets. We are very excited about it. This year we also get funding from ASCC to support our project and also to go to some national competition events. For example, for the rocket team, we plan to build our high power rockets, and then we plan to go to the southern New Mexico for international competition events. If everything go back to normal and if the school remove the travel ban, then this is one of the events we are going to. And in these events, there are more than 100 teams, more than 1,000 students and faculties participate and collaborate on these competition events. And I also want to mention that actually Clark Aerospace is one of the few community colleges that participate in this level of competition events. We have another team, the Joint Plan team. This team is currently working on a joint plane that can do, for example, autonomous flight, remote sensing, or all different kinds of tasks. And this team also plan to go to another competition event in Maryland. By going to this event, you get the opportunity to meet people who have the same passion or the same interest in aerospace program or aerospace project. You also get to network with people from major companies. Actually, if I remember it correctly, over the past 10 years, we have several students who are able to find a job in top companies and organizations such as, say, Intel or Boeing Company and NASA. And we also have students transfer from Clark to UW or WSUV. And when they transfer there, they also get a chance to become a leader for their aerospace program. So there are lots of opportunities we provide in this program, and also lots of opportunity for you to develop yourself so that you can build the skills and the personality and the characteristics that are important for your future jobs. So if you're interested in this program, please let me know. I'm going to type my contact information in the chat. I also forgot to mention that this summer we actually planning for all different kinds of events and trips. For example, we plan to visit Evergreen Space and Aviation Museum. We also plan to visit the museum in Seattle. And we also plan to organize several workshops. And in the workshop, you will get to learn, for example, how to use a software to design a rocket, how to use a software to design a drone plane. And you also get to learn, for example, how to do the 3D modeling and how to use our 3D printer to print the model that you want to build for your project. So there are lots of fun events and activities we are providing here. So if you're interested, just let me know, okay? So any questions about the program? Any questions?
I get the same response when I ask, so.
I'm not surprised.
Yeah.
So if you're wondering about the time, I mean, I get this question from another class. So you're wondering about how much time you need to spend in this program. It turns out usually, it really depends on time. So for example, during normal academic year, you probably will need to spend maybe about 1 to 2 hours with the project. However, as we get closer and closer to this competition event, you might be expected to spend more time on your project. So if that's what you're wondering. And also I would say, through the program, you'll be able to meet, I would say, the best students in Clark College. We actually have a community through which you will be able to work on the project with students, with advisor, with someone from other colleges. We sometimes collaborate with the program, aerospace program from other universities or other colleges. So you get to network with different kinds of people from different kinds of universities and colleges. And so it's a great opportunity for you to learn something interesting and also to network yourself. And this also, actually, I also want to say that this also gives you a chance to build your own portfolio that might be useful when you want to find your future jobs. Any questions? That's okay. If you don't have questions right now, you can always ask me questions through the email. And also we have a Slack channel through which we communicate with each other. And despite the fact that Clark is in the remote operation mode, we still were able to check our materials and tools from Clark so that the students can work on their project. Actually, Nick, if you don't mind, can I share some of my slides?
Yeah, I made you a co-host, so you should be able to screen share.
Oh, okay, great. So I'm going to share one of my slides. Can you guys see my slides?
Yeah.
Right, so these are for example, this is one of the projects that was done by a student using a 3D printer. He was able to 3D print some of the parts for this wind tunnel. This is a device you can use to test for example, your rockets or your drone plane. So this is something that he was able to do during pandemic. And also during the pandemic, we were able to work on our project. So we give the materials and tools to the students so they can build their own, for example, model rockets. And the picture here shows us one of the rocket launch event that we had in Vancouver. That's close to Columbus River. We also, and this is a picture from another team, the John team. They were building, they are using this model, this strong that's made from carbon paper, and they were doing the flight test. Also, we organized trip to, for example, to local companies where students will get to learn, for example, how people use a carbon fibers to build different kinds of interesting parts or interesting tools that you can use. So we give people lots of opportunity to practice and to learn new skills, new technology, and to meet different kinds of people. Yeah. Okay. So if there's no question, I just want to say that thank you guys for the opportunity to talk to you. I look forward to hear from some of you. Thank you.
Thanks, Sophie. Really appreciate it.
Thank you. Have a good class. Bye.
All right, thanks. Talk to you later.
Mm-hmm.
All right, so I don't know how many of you were familiar with the aerospace program already, and many of you are graduating this quarter, and so wouldn't be at Clark after this. It is possible to work with the aerospace program at Clark even when you're not a Clark student, but also I believe WSUV has their own program and does similar things in this area. But this is, to me, you know, one of the most exciting things that that one could get involved with while in college, because I mean it's rockets and it's NASA and it's space and things like that. I've had students get involved with this in the past, and you know you can potentially be part of a team that enters a competition being held by NASA, you know, or JPL, and travel and compete shoulder to shoulder with teams from, you know, MIT or Stanford or Caltech, and you know, go out to dinner with program directors from NASA. And as far as networking opportunities, this can be huge. I mean, it never hurts to practice networking, but you know, you can meet people that can potentially, you know, be a part of where your education, your career goes down the road. And building up your network, you know, is a pretty essential part of the whole process of going through school, because presumably, you know, part of the end game of your education is to go on and get a job and work and make money, and so much of finding a good job and a job where you can really kind of flourish and do the things you want is about networking. And so this is a good opportunity, and the scope of the projects being done by the program are, you know, generally really big, which means lots of different things that need to be done, which means if you're interested in hardware, if you're interested in software, if you are into assembly language programming, if you're into real-time operations, if you're into technical writing, kind of whatever your inclination, there's a good chance that there's some part of the effort that can be that you can contribute to. And it's largely self-regulating. If you want to do this for 40 hours a week, there's almost certainly a way to do that, a way that the project could use you for that many hours. If you want to do this a few hours a week, there's ways you can do that. And project-based learning is the way to go, in my opinion. You've probably heard me say this before. When I was in school, I took a lot of classes. I had some really good teachers, learned some interesting things. All the good stuff I learned pretty much came from doing projects. And they were mostly projects of my own choosing or that my friends and I came up with. And that's where I spent my time. And when I had to, I would pull myself away from those and I'd go to class. Or I'd sit down and I'd do my physics homework, you know, or I'd bite the bullet and go eat a meal, you know, so I wouldn't pass out. But mostly it was doing projects. It was working on things that were appealing to me. So if you got any interest in this, right, definitely check out the Slack channel, talk to Sophie, get some contact info, see what's going on at the club now, and consider segueing to, if you're going WSU, get involved with their program. There's just a lot of opportunity there, and it's part of the fun of school is if you have an opportunity to take advantage of some of these projects, right? Definitely recommend looking at it. All right, that's my post sales pitch. Setting up my new server. Maybe I can carefully transform this into an SLP presentation of some kind, perhaps. Yes. Cool. All right. So any questions, comments on that, or other stuff, PA5, things like that. Set up one for my SLP earlier this quarter, and it was brutal trying to figure it out. Cool. I could imagine several parts that could be brutal. All right. Well, let's continue looking at threads in Java, but also more generally threaded operations. So remember our basic setup. We could begin with a main program, and we could construct a pair of threads. And once we construct these and we start them, they kind of go off and do their own thing, and they're running more or less in parallel, right? And on my system, I've got 4 cores, so my CPU time can add up to 400% theoretically. And when I run threads in Java, my first few threads will actually run in parallel, not time sharing, a slice of time for thread 1, a slice for time thread 2, but they'll actually run simultaneously. And so let's play with this. So here's my main code. It's just a holder for my public static void main. But one thing I'm going to do is I'm going to create a separate object. So I have a class called Go, and Go is where I'm going to do everything, because I'm going to want to put some variables in there, and I'm going to want to refer to them from other objects and so on. And my main method in here is this thing sitting inside a public static void main. And I don't want to get into issues with statics and finals and all that kind of stuff. So I'm just going to construct an object of this class I'm calling Go. And in the constructor for that, I'm going to do all the good stuff I want to do. So this is really just kind of a wrapper to create a Go object. And let's just mess with this. So main thing I'm going to do in Go is I'm going to create a pair of threads, and I'm going to say start. All right, so those are just going to begin a pair of threads. And remember, in my thread, I don't have a method called start, but I do have a method called run. And when I call the start method, start is inherited from the thread class, which my thread extends. And what start does is 2 things. First, it creates a new thread. And then in that new thread, it calls the run method of this object. And so let me just make this a while true. And let me comment out. I don't know if it'll let me do this. Let's just have this infinite loop here. All Alright, so my main program is exiting, but I haven't gotten back to my prompt yet because my threads are still running. So if I do a top, you can see I've got Java taking 200% of my CPU. Those are my two threads, right? And they're not doing anything useful, but they're inside these while loops, and they're just spinning. And 196.7, so pretty much 2 full CPUs until I exit. And if I make 3 threads, right, I've got Java taking close to 300% of the CPU, but it's fighting, right? So my camera and document cam is taking a whole CPU, my window manager is taking a CPU, my screen recorder is taking half, Zoom is taking 40%, and so on. But you can see I've got 3 cores that are really trying to spend their time on my 3 threads. And if I go up to 4 threads, right, I won't get 400% of the CPU because it gets divided down. But for the most part, this is pretty efficient. At least for a few cores. And the largest I've run this on was a 28-core machine, and I used 25 threads running in parallel, and I got 2,500% of the CPU dedicated to my 25 threads, and it was super efficient. Which was really handy. Alright, so let's do something more interesting in here. So we'll do a for loop. We'll go from 0 to 10. We'll print out our integer followed by a space, and then at the end of the loop we'll go ahead and we'll print a new line. Well, that was kind of silly. My syntax checkers are not doing their job. Alright, so we started to look at this yesterday, and in this case, the main program said it was exiting before our threads started printing anything out, and our threads printed out, 0, 1, 2, 3, 4, 5, 6, 7, and then at this point, a second thread seemed to begin, printed out a 0. Here was 8 from the first thread, and then a 1, 9 from the second, 2 from the second thread, and then our new line, and then the second thread finished its output. And as we saw yesterday, right, this will not always do the same thing. It kind of depends on whatever, right, what's going on in the system. But what's happening is, both of these threads are running, but what they're doing at any given time, pretty much unpredictable. And as other things are running on the system, resources have to be shared. Now, if I really had 2 cores that were totally not doing anything, and these could both be allocated to each of these threads, I would probably get a more repeatable experience. But since there's, so many things competing on my system right now anyway, thread 1 might start running, and then at some point the JVM might decide, or the operating system might decide, okay, let's give this job a little bit of time, this thread, and this will execute for a while, and then something else hits a point where it's waiting for some event, so more CPU is freed up, and so on. So pretty much lives of their own at this point. And that's something to keep in mind, but it's not usually a problem. In fact, it's usually the thing that we're after when we're making threaded code. We're not going to thread 2 things that critically depend on each other every step of the way. We're going to thread things where really we just want one thing to happen over here and something else to happen over there. And they're kind of more or less independent. So in PA5, what is this? Well, our main thread is going to be swing, which is waiting for mouse clicks and, redraw events and button presses and so on. And then we have this net thread, which is mostly waiting for events to come in from our network connection. So it's mostly sitting in a, has next line call. And we want that, whenever something is available on the socket, we want it to go ahead and read it and do its thing. And the swing thread, you know, the main thread we're used to, we want that to respond when a mouse is clicked or a button is clicked and so on and so forth. So this part is fine, okay? Things start to get more interesting when we begin to try to share information between threads. So there's a couple of main ways that we can communicate from one thread to another. One is to use something called inter-process communication or control, IPC. But the more common way probably is to use shared memory, to basically just have variables that both threads can access. So we do this in C when we fork, but we leave, you know, some variables around in the memory space of both processes. We can do this in Java with threads. So let's go ahead and try something. So let me make a public integer called tally with a useless comment called count things. And what I want to do is inside the threads, I want to increment the value of this tally. So in here, instead of printing stuff, I want to increment the tally. Now, if I were to declare a variable up here, right, this is not going to be very interesting because when I increment tally, I'm incrementing this inside this object. And what is this object? Well, it could be MT1, it could be MT2. I'm going to have two threads. One is, you know, the run method of MT1, another is the run method of MT2. And if this tally integer is declared as part of my thread, then I have two copies of this. And they're each tallying their own. What I really want to do is somehow have this thread tally up in this integer. Not PJEX, objects. So this is the notion of how we link a thread up to another object. And this will definitely be something that comes up in PA5. If I have, you know, say my J-frame or my J-panel or something that's creating threads, code inside here can absolutely access things inside these threads, right? How? Because it's creating these threads. It's saying mt1 equals new my thread. It could get to a method in there by saying mt1.method. It could get to a field by saying mt1.tally, right? But sometimes we want things in these threads to access something in the object that created it. Or maybe we want something in this thread to access something in another thread. And there's no inherent way to do that. When we are sitting down here inside of my thread, right, there's nothing here that tells us who created us. And so there's nothing in here that lets me get to the tally object of that go object that created us. So here's a trick that you're going to use a lot. So here's a useful trick. It's not even a trick, it's pretty straightforward. When I construct these threads, I'm just going to tell it who I am. I'm going to pass my identity to the constructor. Ah, excellent. I never tried multi-cores on an ESP32. That would be tricky. Yeah, we're getting into semaphores and such. That's good stuff. All right, so remember what the keyword this is. This is I, right? It's the Freudian ego. It's me, right? This is me. So when I use the word this right here, it means, you know, whatever object this is being executed in, which if we're running our main program, we created an object of type Go called G. This means G, right? So it's this object, which means that this dot tally is that thing right there. All right, so what do we do with this? We go inside the my thread and we're going to save that thing that's given to us in the constructor. So I'm going to have an object of type Go, and I'm going to call it parent. And this is going to be the object that created us. And so I'm going to define a simple constructor which takes a single argument of type Go. And you know, I would normally do parent, and then I would say this dot parent equals parent, but I don't want you to get confused on this versus that this. So I'm just going to call the argument par and say parent equals par. So when I do this, when I do that set of code, it takes the argument to my thread, which is this, and it saves it right here. So when I come back from the constructor, inside MT1 and MT2, I have this object called parent, which represents the class of type, the object of type Go that created these threads, which means I can use parent.tally to get to this integer. Okay, why am I doing this? Simply so that I can do the following. Increment parent.tally. Alright, so this is a test bed. So what's going to happen here? We're going to construct the Go object, which is going to create a pair of threads, and then it's going to start them. So it's going to make two separate threads. Each one will start executing the run method, and the run method will simply loop 10 times, and each time through the loop increment this integer up here in the parent class, the Go class. And then I'm going to do the following. I'm going to add a print statement here. I'm going to print out the value of parent.tally. All right, here's the $1 million question. Well, it's not really $1 million. But if we were in class, I'd give you a SpongeBob dollar for the answer. What do we expect this to print? We've got two threads. They're each going to run this run method. What do we expect the output to be? Count to 20. Seems reasonable. So we've got two threads. Each one is going to print this message at the end. Any guesses what each thread is going to print? Or what some possibilities are? Got two copies of this thread running in two separate threads. Each one has a print message at the end. So we should get 2 lines of output. What's your best guess for what those 2 lines of output will be? First will be random, but last will end with 20. It's a pretty good analysis. Because we don't know if the first thread's going to finish all of its execution and print out 10 before the second thread begins, or if, you know, they might both start running at the same time and each keep adding 1, and when the first thread exits, the count's already up to 19. We don't know, but we're pretty sure that the final tally should be 20. So I would go along with that. So let's see what this does. So almost that, except for the slightly weird thing that the first thread that exited reported 20 and the second thread that exited reported 10. But we can just ignore that, right? This looks a little better, 20 and 20. And maybe 10 and 20, maybe that first one was just a fluke. Right? Nothing to see. Just 20, 20, and 10, 20. But there was something weird up there, right? But mostly it's 20 and 20. What if we go to 10,000? What do we expect the output to be? If we didn't know about this weirdness we just saw, what would we expect the output to be if each thread's going to 10,000? Right? We'd expect 20,000. And almost certainly not 10 and 20, but you know, something and 20. 10 and 20, pretty good. Uh-oh. What? So what the heck is going on? And why 14,000 and 16,000 and there's no 20 in sight there? So this will ruin your night sometimes. And if you don't know about this, and particularly if this is in the middle of, you know, 5,000 lines of code, and it's code somebody else wrote or code you wrote a while ago with no comments in it, and you start seeing this kind of behavior, you got very little chance of figuring out what's going on. In fact, you're probably not going to know this is what's happening because you're going to be seeing some weird effect with, you know, something not being initialized or, you know, a null pointer exception or who knows what. And this looks very straightforward, right? 10,000 times increment the value of the tally. All right, so what's going on? So there's a concept called read, modify, write. If you've done Engineering 270, we talk about this inside there. Read, modify, write is the majority of what your CPU does. Read something from memory, change it, write it back to memory. And there's conditionals and branches and so on and so forth. But mostly it's read, modify, write, read, modify, write. The program counter is a read, modify, write. Read the program counter, add 4, write it back into the program counter. This happens all over in the essence of a CPU. And so if I say something like, you know, I equals I plus 1, this says read the value of I, modify that value that you read, write it back into I. Okay? If I say plus plus I, that's doing the same thing. Read the value of I, modify it by adding 1, and then write it back into register or memory location I. If I'm in assembly language or machine language and I say increment I, or, you know, some location, it's still a read, modify, write operation. Something needs to read this value out of a register or out of memory, route the bits of that value through the data path to the input of an adder, send the command to that adder to say increment, take the output part of that adder, and route that back around to feed it back into the register or memory location corresponding to I. The point that the reason this is important is that this is done in a series of steps. It's not an instantaneous thing. It's pretty rare that you have an architecture that actually just increments something in place, unless every memory location has an add circuit built into it. So we read, we modify, we write. Okay, why do we care? What does that have to do with anything? Let's take a look at this parent tally plus plus. And let's make a simplified view of these two threads. And here's our tally, which is initialized to 0. And this says read tally, add 1, write tally. Read tally, add 1, write tally. All right, how does this work? Tally is equal to 0. Let's suppose thread 1 starts executing first. It reads the tally, which is a 0. It adds 1, which is 1. It writes the tally. Tally is equal to 1. Thread 2 starts to execute. It reads the tally, which is 1. It adds 1, which is 2. It writes the tally, which is 2. Everything is great. We can go home. Life works as we expected. Here's what happens at 3 a.m. when you think you're just about done. Tally is 0. Thread 1 says read the tally. It reads a 0. Says add 1. That's a 1. At this point, thread 2 starts to execute. And it says read the tally. Well, that's a 0. Add 1. That's a 1. Write the tally. So it changes the tally to a 1. Thread 2 is finished. Thread 1 goes back and executes. Says write the tally. Oh yeah, that's a 1. And there you go. Your tally is equal to 1. So that's a problem. So this is not specific to RISC, although the way we're breaking these instructions down is kind of RISC-like, reduced instruction set. But this is kind of endemic to whether you're a reduced or complex instruction set. But we usually talk about these things when we're talking about RISC architectures like ARMs or PICs and such. All right. So the problem with this is that when we write this code and we look at it and we say, is this going to do the right thing? We're making an assumption, which is that the value of tally is not going to change from here to here to here. We're making an assumption that when we read the tally here and we add 1 to it and we write it back, nobody else is going to touch that tally until we're done. And the real problem was when we started doing this, we were getting ready to update our tally, but somebody else read the old value and acted based on that. So what we'd like to do is atomize our operations. So think about the Greek notion of atom, right? If you start pounding a rock and you grind it to small rocks and dust and finer dust, and you keep trying to divide it down, how far can you go? And first impression might be you can keep making it finer and finer, but there was this idea that there's a limit to how far you can grind something. Eventually you get down to something indivisible, which was called an atom. And so when we talk about atomizing our code, we're talking about breaking our code into small pieces that cannot be divided any further. And what we'd like to do is we'd like to know that once this chunk of code begins to execute, it can't get interrupted. Because the whole reason this problem comes up is because once we start executing this, we get part way through, and then something else starts running. We're doing all of this, but before we get a chance to write our beautiful new tally, someone else comes along and starts doing something. And this is a real world problem, right? So you know, the kind of classic, one of the classic examples is like a banking system. So here's your bank. And let's say you have $20 in your bank. And here's your ATM. You're going to go up and you're going to pull $10 out. So you want to withdraw $10. So what do? You read balance, subtract 10, and write the balance. And let's say you work for some company and they're going to deposit your paycheck electronically. And so your paycheck is $100, so they want to deposit $100. Well, what should your balance be at the end of all of this? You started with 20, you took out 10, so you were down to 10. Your company deposited 100. You should end up with $110, right? So how does the deposit routine work? Read the balance, add 100, and write the balance. And the same thing can happen. So you go to the ATM, you start your transaction, you say, I want to take out $10. Okay, read the balance is 20, subtract 10, that's 10. And at that exact moment, your company runs their software that deposits your $100, says read the balance is 20, add $100, that's 120, write the balance, 120, there's your balance. And then your ATM software finishes running, which says, oh yeah, write the balance, okay, 10, there you go. And your $100 deposit just disappeared. All right, so how do we deal with this? How do we ensure that once this block of code starts running, nothing else is going to kick in? So here's an idea, use a flag. So this is where we get into things like semaphores, you know, signal flags for warning about conditions. So what could we do? We could put something up here which says, you know, have some Boolean called lock, which we initialize to false. And we'll put a statement up here which says, while someone has the lock, let's just sit here and loop forever. And once nobody's using that lock, we'll say lock equals true. We'll do our business, and then we'll set lock equals false. And thread 2 will start off and wait for lock to be false. And when lock is finally false, it will set lock equal to true, do its business, and then set lock equal to false. So we're taking these sections of code that need to run uninterrupted, and we're adding a locking mechanism around them. So thread 1 starts, lock is false, it's going to set lock to true and begin executing this code. And when it gets down here, if thread 2 starts, it's going to wait for the lock. It's going to say while lock, and lock is true, so it's going to sit here and spin in this while loop until thread 1 finishes its operation, sets lock to false, and then thread 2 can continue. It'll set lock to true, start its operation. And now if thread 1 wants to do this again, it's going to be stuck here waiting for lock to be false, which doesn't happen until thread 2 finishes. Does that make sense? Unfortunately, it doesn't work. It makes sense, but there's a problem. And the problem is, suppose both of these threads start at the same time. And the first thing they do is they each check the lock, and they say, oh, the lock's clear, it's false, nobody's using this. So they both said lock to true, and now they both start executing this code at the same time, and you got the same problem. And the problem now is that this business of checking to see if the lock is clear, and if it is, setting it to be true, that has to be atomic. And if somebody else can interrogate and update the value of the lock while you're looking at and interrogating and updating the value of the lock, then you can still get into this kind of conflict. It's another read, modify, write. So what we really need is an atomic read, modify, write. And it's really hard to do this in software. There's almost always some sort of hardware support, although the JVM is a virtual piece of hardware, so it's a software mechanism in there. But we need some sort of lower level support for atomizing a section of code. And we can do this in Java very easy, and it's one keyword, it's called synchronized. And we did get to that in the morning class, so if you look at the end of that lecture, it's tagged. You can see the synchronized keyword, but we'll talk about that tomorrow also. So we'll resolve this tomorrow. We'll see how to synchronize this code in Java, and then we'll start looking at this problem more generally, and we'll look at a number of things, including what's called the dining philosopher's problem. So this is a problem that Dijkstra came up with half a century ago to analyze concurrency and resource contention in multiprocessing situations. So we'll play around with dining philosophers, and we'll talk about different approaches to dealing with this, and then we'll go on from there. All right, have a good afternoon. I will see you next time.